Welcome students. So here it is Arka sir, and I have come with another and fresh new episode on physics. So if you watch my previous episode, I have discussed about the magnetic effect of electric current. Okay, so where I have discussed about the deflection Oersted experiment, the basic things, simple concept on magnet. Okay, why what is the magnetic line of force, why the magnetic flux never intersect each other, and what will be the deflection of the if conductor is carrying current, then if any magnet is placed over there, then we can see the deflection of the magnet due to the current carrying conductor. So that we have already discussed. So now today moving to the next point on the same chapter. Okay, so let us move. So today we have in the last day we discussed about the Ampere swimming rule. Now today we will discuss right hand thumb rule. Okay, right hand thumb rule. Basically Ampere swimming rule, right hand thumb rule, these all rules actually state the deflection, in which direction the magnet, okay, the magnetic needle will deflect, or any magnet will deflect due to a current carrying conductor. If a conductor is carrying a current, then we can see the deflection from the Oersted experiment. So which direction the deflection will take place, means in which direction the north pole of the magnet will take place and which direction the south pole of the magnet will take place. So that can be determined by Ampere swimming rule, okay, that I have discussed in the previous episode. And here the same is there, right hand thumb rule. So what is right hand thumb rule? So this is student, this is my right hand. So suppose this is a current carrying conductor, clear? So it implies the current is flowing from my wrist towards my finger, okay, and this is the current carrying conductor. So if the four fingers of the right hand, this is the forefinger, if the four fingers of the right hand actually stretch, okay, straight, okay, now what will happen? And the current is flowing from my wrist towards the finger, then what will happen? This will be what? This will be the thumb, okay. So the thumb will represent, if we stretch our hand like this, then the thumb will represent the deflection of the north pole of the magnet, clear? So this is the right hand thumb rule. So if we stretch our right hand, clear, and if this is the current carrying conductor and current is flowing from the wrist to the finger, then what will happen? The thumb will determine the deflection of the north pole of the magnet, clear? So this is the right hand thumb rule. So what is that? If we stretch the four fingers of our right hand except thumb and a current carrying conductor is kept under it, such as the current is flowing towards the tip of the finger, then the thumb will represent the deflection of north pole of magnet. Clear? So now So I am telling it once again. If we stretch the 4 fingers, okay, and if it a current carrying conductor is placed near beneath it, then what will happen? If the current is flowing towards the tip of the finger, then the thumb will represent the deflection of the magnet, deflection of the north pole of the magnet. So from these two laws, the previous law I have discussed in the previous episode, Ampere swimming rule, and this is what, right hand thumb rule. So from these two laws, what we can understand? We can understand, or we come to know the deflection of the magnet due to a current carrying conductor. If a conductor is carrying a current, then what should be the direct deflection of the magnetic pole? Clear? So this is also known as the right hand thumb rules. Clear? So now moving to the next. So next topic is now what we come to know, that magnetic line of force is there. Okay, so when a current carrying conductor is also carrying a current, when a conductor is carrying a current, then what will happen? Then the electric field will be generated. So just like the magnet, the electric line of force, the electric flux will be there, okay, around it. So due to this electric flux, okay, the electric field will develop, okay, around a current carrying conductor. Clear? So this is the electric flux, just like the magnetic flux. The properties are same. Just like the magnetic flux, the electric fluxes are there. The property of the magnetic flux as well as the electric fluxes will be same. As well as the current will flow through this conductor, the electric flux will also exist. And due to the electric flux, actually the electrical field, okay, around this current carrying conductor will be generated. Now what will be the direction of the electric flux? Okay, what will be the direction of the electrical line of force or electric flux? Okay, so that we can determine also by the laws. So first law is known as Maxwell's corkscrew rule. Maxwell's corkscrew rule. So this is the law. So what we come to know from this law? We come to know the direction of the electrical flux or magnetic line of forces. What will be the direction of the magnetic line of forces? We cannot determine the deflection of the magnetic pole. The deflection of the magnetic pole due to a current carrying conductor can be determined by the two laws. First law is Ampere swimming law, and second law is right hand thumb rule. Just I have discussed. Okay. And here how we can determine the direction of the magnetic flux, okay, or electrical flux due to a current carrying conductor. What should be the direction? So first law is known as the Maxwell corkscrew rule. So this is the first law, Maxwell corkscrew rule. So suppose this is a current carrying conductor. Now screw means what? Either it will be anti-clockwise, or left turn will be there, or right turn will be there. Clear? So if a screw is there, and suppose the screw is right turn screw. Clear? So right turn screw is there. Okay, so we have to move the screw like this. Clear? So now what will happen? If the current is flowing from this direction, so if imagine this is the screw, and this will be the turnings of the screw. Okay, the screw will turn like this. Okay, so that means what? The direction of the, this will be the direction of the movement of our thumb. Okay, so this will be the movement of our thumb. So if we hold, okay, the conductor, clear? If we hold the conductor with the 4 fingers, okay, or the screw, and if it is a right turn screw, then what will happen? The movement of our thumb, will imply or will indicate the direction of the magnetic line of force. Clear? So if we have a screw, right turn screw, which will work on right turns, and if we hold the screw with the 4 fingers as well as the thumb will be in straight, then what? then the movement, okay, if we just doing like this, okay, then the movement of the thumb will imply the direction of the magnetic line of force. Clear? So that is what, that is Maxwell corkscrew rule. So what we can write, if a right turn screw indicates the direction of electric current through a conductor, then the movement of thumb will indicate the direction of magnetic line of force, magnetic line of force. Okay, so what is magnetic line of force? So that is what Maxwell corkscrew rule. So if a right turn screw is there and it will indicate the what, direction of the electric current, okay, through a conductor, then the movement of our thumb will actually indicate the direction of the magnetic line of force, okay, the direction of the magnetic line of force. So this will be the direction of the magnetic line of force if the current is passing from A to B. Clear? If the direction is reversed, then it will also be reversed, then what, it will be the direction. Clear? Just the opposite. Clear? So this is what, the Maxwell corkscrew rule. So next, the same thing, things, what we can, another law is there. So that is known as right hand grip rule. Right hand grip rule. Clear? So from this law also we come to know, we can come to know the direction of the magnetic line of force. Clear? Or the direction of the electric flux. Clear? Or magnetic flux. We can come to know the right hand grip rule. Very easy. So suppose this is my right hand. Clear? Suppose this is the current carrying conductor. Okay. So if we hold the conductor with the grip the conductor with the 4 fingers. Clear? With the 4 fingers of our right hand. Clear? And if the thumb indicates the direction of flow of current, then the direction of this 4 finger will be same to the same as the direction of the magnetic line of force. Clear? So this grip, the direction of this grip, if the thumb is indicating the direction of the, if the thumb is indicating the direction of the flow of current, then this grip will indicate the direction of the magnetic line of force. Clear? So this is known as right hand grip rule. Clear? So from the two rules, the Maxwell's right hand rule, okay, corkscrew rule and the right hand grip rule indicates the what, direction of the magnetic line of force. So what is the right hand grip rule? If we hold a current carrying conductor with our 4 fingers of right hand except thumb is indicating the direction of flow of current, then the grip of four fingers will indicate the direction of magnetic line of force. Clear? So this is what? This is known as the right hand grip rule. Clear? So what is that? Again I am explaining. So if we have, this is the right hand, this is the four fingers, and if we hold a current carrying conductor like this, and the thumb is indicating the direction of electric current, flow of electric current, then the direction of the grip of the four fingers will indicate the direction of magnetic line of force. Clear? So if we draw, so this is what? So, and this is the thumb is indicating, so what will be the grip? Direction of the grip will be like this. The direction of the grip will be like this. So this will be what? This will be what? The magnetic line of force. Clear to all of you? So this will be the direction of the magnetic line of force. So students, hope you have understand this. Clear? You have understood this. So now let us move to the next topic. So students, now the next topic is the pattern of magnetic line of force due to straight current carrying conductor. Okay, it is very easy. So now suppose this is the boat, okay, and suppose this is a straight current carrying conductor. So now right hand grip rule, this is the, suppose this is the conductor, okay, it is current, so the grip will be like this, okay, or Maxwell, okay, corkscrew rule, okay. So this will be what? This will be the direction of the magnetic line of force. So if a straight current carrying conductor is conducting current from this to this, from suppose it is A and it is B, from B to A, clear, then the all the magnetic line of force will be concentric circles. That means their center will be same, clear, it will be concentric circles, clear, and the direction will obey the right hand grip rule or Maxwell corkscrew rule, clear. So this will be the pattern of the magnetic line of force due to a straight current carrying conductor. So how we can experiment that? We can put some dust of iron dust, clear, okay. So the current let the current will be passed to this, and if we just shake it a little bit, then the other part, the dust will fall down, clear, and it will take, we can observe the circular shape, and each circular shape will indicate the magnetic line of forces, and the direction will obey the Maxwell corkscrew rule or right hand grip rule. Clear? So this will be the pattern of the magnetic line of force due to a straight current carrying conductor. So now moving to the next topic. Moving to the next topic. Pattern of magnetic line of force due to a circular loop. Okay, due to a circular loop. Okay, so see, clear. So suppose this is a circular loop. Okay, so now here a board is there. Okay, so this is a circular loop, it passed. So from, if we see this cases, so here the current is flowing from what? Bottom to towards top. Clear? So what? The right hand grip rule or corkscrew rule. Okay, as per that, what will happen? So the direction of the magnetic field will be this. And here in this case, and it will be just like straight current carrying conductor, it will be concentric circles. Clear? For this arm. Okay, for this arm, what the current is flowing in opposite direction. Here it is from bottom to top, and here it is from top to bottom. Clear? So the direction will be here, it will be like this, and so here it will be opposite. Okay, so it will be opposite direction. So it will be also the concentric circles, but the directions will be opposite. Clear? Now see, at the almost at the middle, the lines, the directions will be same. Clear? For these two magnetic line of forces, the direction will be same, and almost they are almost parallel to each other. That means here we can have a uniform magnetic field. If the magnetic line of forces are parallel to each other, then we can get a uniform magnetic field. So towards the middle of the board, okay, due to the current flowing through this circular loop, clear, the magnetic line of forces will be almost parallel to each other, and we will have a uniform magnetic field. So here we will get a uniform magnetic field. Clear? So both the arms, it will be the concentric circles will be there, having the same center of the circle. Here also the center will be same, but the direction, here the current is flowing from bottom to top, and here it is flowing from top to bottom. The direction of the magnetic line of forces will be opposite. Clear? And it will obey the right hand grip rule or Maxwell corkscrew rule. Clear? So this is how, so student, I hope you have understood up to this. Clear? So what is the Maxwell corkscrew rule, what is right hand grip rule, and what will be the direction of the magnetic line of force due to a straight current carrying conductor and a circular loop, clear, which is conducting a current electricity. Okay. So now let us move to the next topic. So students, now let us move to severt law or Laplace law. Okay, both are same. So severt law or Laplace law. So suppose it is a part of a conductor, circular or semicircular, whatever. Clear? It is a part of the conductor. Suppose A and B. We are considering only a part of the conductor, and we are taking, so total length suppose is L, but we are taking a small length, suppose it is delta L. A small part of the conductor we are considering. Clear? Suppose it is delta L. Okay. So now what will happen? We have to find out the magnetic field intensity at this point due to this current carrying conductor, okay, or due to this small length L. So this is the direction of the magnetic field, and suppose this angle is theta. Clear? No, now the thing is that so suppose magnetic field intensity is delta B. For the length delta L, the magnetic field intensity is delta B. So what is the first thing? First, the magnetic field intensity is directly proportional to the length of the conductor. Okay, length of the conductor. So what is the length? So delta B will directly proportional to delta L. Clear? So the magnetic field intensity will be directly proportional to the length of the conductor. If the length increases, then obviously the magnetic field intensity will also increase at a point. Okay. Now number 2, the magnetic field intensity is directly proportional to the flow of electric current. That is, if the current is flowing I, so what? Delta B is directly proportional to I. Clear? So the magnetic field intensity is directly proportional to the flow of electric current through this conductor. Clear? The flow of electric current through this conductor. So this is the current is flowing I. So delta B is directly proportional to I. Now number 3, the magnetic field intensity is inversely proportional to the square of the distance between the conductor and the point in the field. That means suppose if this distance is r, then what we can write? Delta B is inversely proportional to the distance square. Clear? So the magnetic field intensity is inversely proportional to the distance between the conductor and the point in the field, okay, or inside the field. So delta B will be inversely proportional to 1 by r square. Now number 4, the magnetic field intensity is directly proportional to the sine of angle between the magnetic field direction and the distance between conductor and the point inside the field. Okay. So suppose this angle is theta. This is the for this point. If we draw the tangent, so that will what? That will, it is a magnetic line of force. So the tangent from this point will indicate the direction of the magnetic field. Clear? So to the direction of the magnetic field, and this is the distance. Okay, the between the conductor or between the magnetic line of force. Okay, clear, or conductor and that particular point. Clear? So this angle is theta. So it will be directly proportional to the sine of this angle. So delta B is proportional to sine theta. Clear? Directly proportional to sine theta. Clear? So now if we combined these 4 laws, then what we can write? Delta B is directly proportional to delta L into sine theta into what? Sine theta into I divided by what? R square. Clear? So what we can write? Delta B is equal to K into delta L sine theta into I by R square. Clear? So where K is a constant. Clear? Where K is a constant. So now what we can write? Delta B is proportional to delta L sine theta into I. So delta B is equal to K into, we are omitting the various sign. So K into delta L I into sine theta by R square. So K is a constant. Clear? So this is known as the Severt's law. So I am rubbing this. So this is known as the Severt's law. Now, so what we can write? Severt's law. So what we can write? What we have seen? Delta B is equal to K into delta L into I into sine theta by R square. Now K is a constant. K is a constant. Now for K is a constant. Now what we can write? What we come to know? K is equal to mu 0 by 4 pi, where mu 0 is equal to permeability of free space. Clear? Permeability of the free space. Okay. So now what we can write then? Delta B is equal to mu 0 by 4 pi into I into del L sin theta by r square. Clear? So where mu 0 is the permeability of the free space. Clear? So this is the thing. So delta B is equal to mu 0 by 4 pi into I del L sin theta by r square. So this is the standard form of Severt's law, or this law is also known as the Laplace law. So student, hope you have understood the Severt's law. I explained it point to point. Okay. So if you can remember this equation, then you can easily write the laws. How? Because when these all are fixed, then delta B is directly proportional to I, means flow of current to the conductor. Now delta B is proportional to del L, that means the small length of the conductor. Now del B is proportional to sin theta. Okay, theta is what? The angle between the distance of the conductor as well as the point as well as the field direction of the magnetic field. Clear? And r square. R means what? The distance between the conductor and the point. Okay. So if you can only remember this equation, you can easily write the formula. So the value of K will be mu 0 by 4 pi, where mu 0 is the permeability of free space. So this is the Severt's law or Laplace law. Hope you have understood this. Now let us move to the next topic. So students, so hope you have understood this. Clear? So delta B is mu 0 by 4 pi into I delta L sin theta. I means what? The flow of current. Delta L means the small length of the conductor. R means the distance between the point and the conductor, and theta is equal to angle between the direction of flow of current and the distance between the conductor and that particular point. Okay. Now what will be the unit? Now let us determine the unit of delta B. The unit of delta B. So what do we know? Delta B, it is the unit. What will be the SI unit? Delta B is equal to I into delta L sin theta. Here it is mu 0 by 4 pi divided by r square. Clear? So mu 0 and sin theta, no unit is there. 4 pi is also constant, no unit is there. I means what? Ampere. Delta L is equal to meter, and R is equal to what? Meter square. Clear? So what we know? Delta B is equal to ampere into meter, okay, divided by meter square. So ampere, so it is what? Ampere per meter. It is also known as Weber per meter square. Okay, ampere into meter means Weber. Okay, ampere into meter means Weber. So ampere by meter, or ampere into meter means Weber divided by meter square. So Weber per meter square. Clear? The unit of delta B. The unit of delta B is what? Weber per meter square. Clear? It is also known as Henry. Clear? Now what will be the unit of mu 0? Unit of mu 0. What we know? Delta B is equal to mu 0 by 4 pi into I into delta L sin theta by r square. Okay. So that means what? Mu 0 into I into delta L sin theta is equal to delta B into 4 pi into r square. Clear? That means mu 0 is equal to what? Delta B into 4 pi into r square divided by I into delta L into sin theta. Now sin theta and 4 pi don't have any unit. So delta B means what? Weber per meter square into R means what? Meter square divided by I means what? Ampere into meter. Clear? So this meter square we cancelled. So it is what? Weber per ampere per meter. That means what? Weber, we can write Weber meter ampere to the power minus 1 meter to the power minus 1 Weber per ampere per meter. Clear? So this is the unit of the permeability of the free space. Okay, Weber per ampere per meter. Clear to all of you? Now hope you have understood up to this. Clear? So now move to the next topic. So now let us move to the next topic, magnetizing field. Magnetizing field. So what we know from Weishaber's law? Delta B is equal to what? Mu 0 by 4 pi into I into delta L sin theta by a square. Clear? Here mu 0 is equal to what? Permeability of free space. Let mu is equal to permeability of any medium. Clear? The permeability of medium mu will differ from medium to medium. Now what we can write? Delta B is equal to mu by 4 pi into I into delta L sin theta by r square. That means what we can write? Delta B is equal to mu into 1 by 4 pi into I into delta L sin theta by r square. So what we can actually see, mu 0 or mu whatever, okay, 1 by 4 pi is constant. So this will same for all the medium, 1 by 4 pi I delta L sin theta by r square. That is what? Fixed for all the medium. Only this value, the value of mu, permeability of any medium, that will change. It will differ from medium to medium. Clear? It will change only. Clear? But this part does not depend upon the medium. It is same for all the mediums. Okay. So this is known as the magnetizing. This part is known as the magnetizing field. So delta B is equal to mu into what? So delta H. Clear? Delta H is known as the magnetizing field. So now what we can write? Delta. So suppose it is for the small portions of the conductor, the small portions we have taken. Clear? So now if the total for the all full length of the conductor, the total magnetic field, okay, B is equal to mu into H. H means what? Magnetizing field. H is equal to magnetizing field. Okay, magnetizing field. So what we can write? So H is equal to B by mu. Clear? H is equal to B by mu. So B is the what? Magnetic field intensity and mu is equal to permeability of any medium. Clear? So B is equal to what? Magnetic field intensity and mu is equal to permeability of any medium. Clear? So what we can write? So magnetizing field, what you can write in a definition? Magnetizing field H is equal to B by mu. So it is the ratio of the magnetic field for the total current carrying conductor to the what? To the permeability of that particular medium. So what we can write? The magnetizing field of a medium. The magnetizing field of a medium is the ratio of the total magnetic field due to the current carrying conductor to the permeability of that medium. So this is known as the magnetizing field. So what we can write as a definition? What we can write as a definition? Okay. So it is the ratio of the magnetic field due to the current carrying conductor to the permeability of that particular medium. Clear? So this is known as the magnetizing field, clear, of a particular that particular medium for a current carrying conductor. So students, so hope today episode you have understood the Severt's law and the different laws, the Maxwell corkscrew law, right hand thumb rule, as well as the right hand grip rule, clear, and Severt's law, and what is the permeability of medium. Okay, so permeability of any medium or permeability of free space, so that, and what are the units of that, clear. So that all we have discussed. So in the next class I will do some little bit of theoretical portion, and then we will come to the numeric problems, okay, on this topic. So very important one. So if you have any queries, then write to me, clear, so in comments, so I will clarify that. So see you in the next episode. Thank you.